Hello everyone, my name is Suen Pai from the Empathic Computing Laboratory of the University of Auckland, and today we'll be presenting our project entitled NeuralDrum, Perceiving Brain Synchronicity in XR Drumming. So just sit back, relax and enjoy. So I'm going to start off by explaining a little bit about what brain synchronicity is, and in short, it's simply when two or more individuals have their brain activations in phase, which I will later explain how we calculate this phase information. And the methodology of which we collect these signals of our brain when it's synchronized is called hyperscanning, which was coined by Montag in 2002. However, up until now, there's actually very little work when it comes to evaluation of hyperscanning or brain synchronicity in mixed reality environments or XR environments. And also, there's not much work about the possibility of brain synchronicity being perceived by the users themselves when they are actually experiencing it, which we think is rather interesting in this research. So the goals of this work is threefold. Firstly, we would like to look into blending cognitive neuroscience, immersive AR/VR experiences in a closed feedback loop. We also like to understand the ability of users to perceive the brain synchronicity, and we could like to see if this could be used as an advantage for the system, as well as introduce the use of hyperscanning for future collaborative XR and HCI research. So looking at past related works, I'd like to divide this into brain synchronicity and collaboration in VR. Looking at brain synchronicity, hyperscanning was first actually introduced in 1965, but the term was later on only coined by Montag. But the first actual research paper with brain synchronicity is actually since 1965. One of our more recent works on hyperscanning is by having two users perform a finger pointing task in which one user directs another user as he moves the hands around, and the other user just follows the finger with full attention towards the position of the hand. And it was revealed that this synchronous movement actually creates brain synchrony, which we think is quite interesting. Besides that, hyperscanning has also been studied in applications like flight simulator and even card games, because you can imagine that if we are able to actually quantify how synchronous people can work with each other, you can actually leverage this as a benefit towards quantifying how well, how effective a system could be, or how efficient people learn how to use such a system, which is something that we are also doing in this study. Looking at collaborative VR environments, so shared spaces in VR have allowed for many collaborative possibilities, mainly due to how it allows us to do many kinds of input interactions, such as using gesture, motion, sensing, even using physiological signals, other kinds of signals like skin conductance, heart rate, and so on. So yeah, for example, VR experience will leverage signals like heart rate for applications like collaborative gaming. I think you actually see this a lot in sort of horror games, actually, collaborative horror games, or even tasks where you need to complete together and you can monitor each other's heart rate to see how efficient each other are. So looking at our implementation, we rely on electroencephalography, which is brain signals. In our case, we created this EEG headband using the OpenBCI board actually, but we just focus on the prefrontal cortex of the user. So it's just basically on the forehead, similar to how Luxi Labs implement their system. So it's basically on FP1, FP2 location according to the 1020 electrode standard placement. Not only that, we focus on the theta band. So EEG signals are divided into several bands. We focus on the theta band, which lies between 4 to 7.9 gigahertz, which is meant to detect arousal and mental load. To analyze this, we use a sliding window of 500 samples with a bandpass filter to filter out the theta band values. And earlier I mentioned that we use some phase information to find if someone's brains, if the participants' brains are synchronized. And that's actually through something called PLV, or the phase locking value, which is used in a lot of past related works to calculate brain synchronicity. So by calculating PLV, we actually get a range of values from 0 to 1, with 1 signifying maximum synchronicity and 0 meaning low synchronicity or almost non-existent synchronicity. So the diagram on the right side basically just shows the rough system where we actually have two users linked to a VR-ready laptop playing the environment, in which the information from another machine which processes the EEG data is streamed towards. The setup is the headband as well as two drumsticks which I will explain a little bit later on. Looking at the implementation for the XR side, we built the XR environment using the Unity engine and viewed it with the HTC Vive head-mounted display. Not only that, we also used the Intel D415 depth camera attached to the front of the headset for XR particle effects, and also used actually as a way to create a closed feedback loop. For the haptic sensation, we used just simple everyday objects placed on the table with virtual drums overlaying the objects, so that for the user, when look at the drums, they see the virtual drums as opposed to the everyday objects. But when you hit them, you feel the haptic sensation. The drumsticks, as shown from the previous slide, are also tracked with Vive pucks, and they are just made from monopods with plush toys attached at the end to dampen the impact as you hit the tabletop items. So a simple diagram here shows how the VR ready laptops are connected to each of the HMDs. So there are 2 HMDs placed there for each of the users, and then we calculate their brain signals through the headband at the same time. So the way how the game works is that it's very closely inspired by popular rhythm games these days, like Beat Saber, which I'm sure many of you have heard of, but also Taiko Drum, which isn't a VR game or any of the sort, but it is a famous game where you actually get to play a drum connected to a gaming console, where it's a rhythm game basically, where you have a set of drums to hit according to rings. So we implement it the same way, in which case, when you look at the drums around you, there are rings falling down towards each drum. And when a ring touches the surface of the drum, it indicates that that's the time for you to hit that specific drum. So in front of each user, there are actually 4 drums in front of them. So the rings will just keep falling down and just hit the rings when it touches the drum. However, the score of the user or how well they perform doesn't depend on actually how well they hit the drums, but it's more towards their PLV value. So the higher their synchronicity or the lower their synchronicity, this will affect their experience. And NeuralDrum changes the skybox, particle effect, audio quality, as well as the see-through behavior, which is why we had the Intel D415 camera. If you look at the image to the right side, when the synchronicity is low, they could actually see the opposite user more. And so they could see the motion of the opposite user a little bit more clearer. And as it becomes more synchronized, particle effects will improve and become more immersed in the environment, and the see-through becomes less. If at any time their PLV drops, then they get to see through again. So this creates actually a closed feedback loop where the PLV affects the experience, which also affects the PLV at the same time to create an improved experience over time. So we conducted a pilot study during SIGGRAPH Asia 2019 XR demo, which is last year, which took about 5 minutes for each user. So it's done in the public. So we just request that they maintain a stable facial expression and avoid speaking when they join the experiment. But we didn't enforce this, obviously. It's just for the entertainment of the user. An experimenter will play as a second player to mirror the opposing motion of the user, similarly like the finger pointing task, but in this case, we use a drumming environment. And then after the experience, they just answer a 7-point Likert scale questionnaire for qualitative feedback analysis as well. And overall, we collected 40 participants, but then we reduced that to 26 because some of them had excessive noise in the data as well as some logging issues. From our results from the questionnaire, we found that a synchronicity was actually not easily perceivable. I'm looking at some of the Q1, Q2, and Q3, so there's a list of the questions over here. And we think that this could be possible due to the game actually requiring concentration. So most people are actually concentrating on the task as opposed to the synchronicity, brain synchronicity. So that could be one of the reasons, looking at the result of Q5. And even though Q1 was high, which is their feeling of connectedness, it was quite spreaded in terms of the interquartile range. However, looking at the feedback of the user, many of them enjoyed it. So some of the notable feedbacks, positive feedbacks, include, say, P4 saying that it feels synchronized and it feels like they could accomplish a task together. P9 says that there's a motivated effect. They felt connected, and at some point they forgot they're actually drumming with the opposing player. And P22 had a great feedback because he or she said that he felt like his body was exchanged with the partner, which I think is very interesting. For the constructive feedback, P8 mentioned that he prefers to be a louder sound when hitting the drums, less distracting particles. As for P10, apparently he feels the screen looked darker when the brains are not synchronized, and he or she feels that overall synchronization feedback could be clearer. Bit of the analysis, we also found that bad players generally have more erratic plots on this side, the left side at least, and bigger dips in the PLV with an overall negative trend of the PLV over time. Whereas looking at the good players, which is over that side, the other side, had more consistent PLV with overall positive trend. So PLV is directly based on EEG, which is affected by a person's attention, motivation, mental state, and so on. Several variables out there. And that brings me to the end of my presentation. Thank you very much. And I'll now be accepting questions.